This is our first application framework, the Internet search engines. I'm going to give you some background and a simple example to get started. We're talking about Internet search, and of course when you think about Internet search, you think of Silicon Valley, which is in San Jose, California, right outside of Stanford and close to UC Berkeley. It's an offshoot of Stanford. It was actually the Stanford Research Park. David Hewlett and John Packard, 1953, started Hewlett-Packard. Xerox, Yahoo moved there also. And John Dykstra of UC Berkeley, whose methods actually led to the special effects in the movie Star Wars. And these two guys. So who are these two guys? This is Larry Page and Sergey Brin. They were collaborators in doing PhD research in computer science, in which they wrote the paper from their PhD research called The Anatomy of a Large-Scale Hypertextual Web Search Engine, which formed the basis for a new company. And this is the actual original site for Google. And their paper led to a new way of doing search engines, or searching the web. Now this was a very big deal because search engines usually fail. They mostly fail. The dot-com bust of the late 90s was really a failure of a lot of search companies. Here are the search engines that were around in the 90s. There's a lot of them. I'm not going to go through all of them. Most all of them are now gone. Why did Google succeed where so many others failed? Well, they developed a thing called the PageRank system. Some features are still trade secrets, but there are some general practices that we'll actually look at this semester. One thing to keep in mind is search engines are still maturing. They're still trying to get it right. Nobody yet believes that the search engine has arrived. So we're going to explore how linear algebra models a network of web pages, and by the end of the semester, we'll see one of the secrets behind Google's paid search algorithm. I'll give you a hint, it uses some very abstract mathematics. So framework one is we're going to have search engines which are based on bots. Bots run around from page to page. They get the page's information, they count the number of links to other pages, and then they randomly choose one of those links to go to the next page. They move very fast. There are at least a few thousand operating at any given time, and a bot, again, is an automated web user, a program that accesses web pages. Now, we'll make some assumptions, and the bots have to implement these assumptions. They have to move randomly from choosing the links on the current page. They have to move ergodically, which means they have to fill a network. They can't just all ring around some little small part of the network, ignoring a whole large other part. And they will have to also reach an equilibrium, and we'll see that momentarily. Now we're just going to look at a very simple example to begin with. Suppose we have a network with 3 web pages. And if there are 10 links on page 1 and 8 of them point to page 2, there's an 80% chance of going from page 1 to page 2 and a 20% chance of going to page 1 to page 3. And here's our transition diagram. Notice that we won't ever draw the edges going from a page to itself because we can figure those out by simply subtracting the outgoing probabilities from 1. So we can get the probabilities from going to other pages, and so here we have a 3-page network and the probabilities of going from page to page within this network. Now a natural question is to ask which of these pages is the most popular. In other words, which is the highest ranked. Now we're going to assume a constant number of bots, 1,000 in this case. Before transition, we're going to say that there are X bots on page 1, Y bots on page 2, and Z bots on page 3. After the transition, there'll be 0.4Y bots on page 1, the ones that came from here along this edge. 0.8X plus Z will be the ones in 2, so there'll be 0.8 coming from here, and all of them in 3 will be coming from this direction. And 0.2x plus 0.6y, that's 0.6 here and 0.2 here, that reach page 3. Now, if the bots move from page to page within this network, then eventually, hopefully, they'll reach an equilibrium. Equilibrium, again, means the total bots on a page is constant from one transition to the next. So departing bots are replaced by the same number of arriving bots. It's approximate, but it works very well if you've got a large number of bots running around for a long period of time. So before equals after means x equals 0.4y, the before and after. Y is 0.8x plus z, and z is 0.2x plus 0.6y. And there are 1,000 bots in the system, so x plus y plus z, the total number of bots, is 1,000. Equilibrium means a system of equations. Notice here we have a system of equations. We can subtract and get all the variables on one side, and this is what we're used to seeing in our textbooks, for instance. So the largest solution, the page with the equilibrium most number of bots at any given time, is going to be the most popular page. So we've got 4 equations and 3 unknowns. We'll use 3 of the equations and check with the 4th. So we substitute 0.4y into here. So notice here's an x here. So we're going to replace this x by 0.4y. You see that here. And when we multiply, that's 0.08. And so we get 0.08y plus 0.6y. And so z is 0.68y. Now we can substitute these 2 quantities into the x plus y plus z equals 1,000. And here you see us doing that, 0.4y plus y plus 0.68y equals 1,000. Now we know that y is 480.8. Now remember, this is equilibrium, so this is the average on the page at any given time. So sometimes there's 480, but most of the time there's 481, and it averages out to 480.8. Then if you let y equal 480.8 and x equals 0.4y, remember that gives us x is 192.3, and then we plug in the 480.8 to the 0.68y, and we get z is 326.9. And notice that means that page 2 is our most popular page, the one where most of the largest number of bots congregates during equilibrium. So there's our solution. There's our most popular page. And now we can check it out by plugging it into the unused equation. This solution actually does work. So equilibrium is system of equations. So we didn't have to do all the substitutions. We could actually set this up as a big matrix and use a matrix to solve. Now, 4 equations with 3 variables has a solution only if one of the equations can be ignored. Remember that. That is going to correspond for us to having a row of zeros. Now we're ready for the next video. This will be another example, more involved example, and this will be on this YouTube site as well.